Am I audible, Afroza? Good evening. Please write something in the chat so that I can understand that you are listening and I'm audible. No. Okay, fine. Jabana is here. Good evening, Jabana.
Good evening, sir.
Are you in contact with Afroza by any chance?
Okay, I'll message her, sir.
No. She's in the meeting. I'm just ask her the next time that is she able to listen or not? Because I cannot see the audio connected icon adjacent to Afroza. Okay, yeah, fine. So we were studying about resonance, resonating structures, resonance, and we were on the second case of resonance, that was pi, sigma, and then we had a lone pair. We had a lone pair electron. So the example that we were seeing was CH2, single bond, CH, and wait a second, this will be double bond, A double bond B, single bond C, and C has a lone pair, and then NH2. NH2 will be having a lone pair. The electrons movement will be like this. We'll make the resonating structure symbol with a double-headed arrow, and we will give a negative charge here because the carbon is getting electrons. So a negative charge here. This will become a single bond because the pi bond has now been broken. This will be CH, and this will be double bond. This will be NH2. And since nitrogen has started to share electrons with CH, it will gain a positive charge. It will gain a positive charge because it has more it has been sharing a pair of electrons with carbon. Now it has 4 bonds, hence it will have a positive charge. Another example of this would be yes, CH2 double bond, CH single bond, OH, and OH has 2 lone pairs. So this will be, what will be this? This will be again same thing, movement of lone pair from here to here, and this will be CH2 negative, single bond CH, double bond O and H. Now when oxygen has 3 bonds, it will get a positive charge. It will get a positive charge. It will get a positive charge. Okay, that's very similar to this case. Very similar to this case is the case of pi, sigma, and negative charge. Pi, sigma, and negative charge. It means that we will have something like AB, single bond C, and we will have a negative charge here, and we will have a negative charge here. So the same type of thing will be happening. For example, if I have CH2, double bond CH, single bond CH2 negative, and this negative is always will be having a lone pair here. Okay, but if somebody has some element, some atom which is neutral generally, now it has a negative charge. That means it will have a lone pair electron, even though if we don't show this lone pair electron. Now this negative charge will fall down here, and this will go here, and we will have a resonating structure like this, CH2 single bond. Now this will be having a lone pair and negative charge, CH, and double bond CH2. Okay. Similarly, we will be yes. If we have this structure, this is negative. This is negative. Nitrogen is positive. Now A double bond B, A double bond B, single bond C, and C has a lone pair. Correct? So How can I make structure like this? We can make structure like this, single bond O, and this will go here, this will go here, this will be negative charge, this will be negative charge, this will be, this is positive, this will be double bond O. And similarly, you can make others also. The important, Acha, Froza's internet is very unstable. But so you are just seeing a. Acha, fine. Jubena has asked. Jubena, can she listen?
So she didn't respond to me.
Acha, she has just. Did you ask her something?
Yes, sir, I asked.
Acha, fine. She has messaged me, by the way. Sorry, sir. Sorry, sir, unstable internet. I guess that is why she has not connected. She just watching things. Okay. Jubena, the one thing that you should note here is that, can you tell me what, do you see any charges here in this particular molecule?
No, sir.
No charges, correct? That means the total charge is equal to
0.
0. What about here? What is the total charge here?
0.
Total charge, I am writing Q for charge is equal to 0. Similarly, here, what is the charge? 0. Here also
0.
0. And what is the charge here?
Minus.
Minus 1. What is the charge here?
Minus 1.
Minus 1. So one thing that we should note now, is that all the resonating structures, now let me just shrink this a bit. All the R dot S dot. What is R dot S dot? It is resonating structures should have equal total charge. Correct? Equal total charge. That means the total charge on all resonating structures, should be equal. Total charge, better wording would be that only, total charge on all resonating structure should be equal. Okay. So Jubena, you can copy this and let me know when you are done. We will move on to the next case. Is there any music kind of thing from my side?
No, sir.
Okay, fine.
Sir, as it 1 minute, sir. Okay. So as it moved from lone pair, it just moved from single bond, and from single bond to double, like double bond changes into CH2. It's like sign is passing, right?
Yes, the electrons are moving. Electrons are negatively charged, correct?
Yes, sir.
So electrons are moving, sign is passing. Don't remember it in that way. You just remember that electrons are moving from electron source to electron sink.
So
correct?
As it moves, it turns into positive, right?
Where?
In first one.
Here?
Yeah.
Yes, this is lone pair na. Okay, fine. Let me just tell you. Wait a second, okay. If I say NH3, can you tell me what will be the charge on nitrogen? Formal charge, do you know about? Do you have any idea on formal charge?
Negative.
Okay, no, not negative. Okay, fine. Let me just give you an idea about formal charge. Formal charge, okay. Now, what is formal charge? Formal charge is formal charge. What is formal charge? Formal charge is just go by the name. It is formal. Don't believe it in it so much. Okay, just one heads up. Now tell me how many electrons are present in here in this nitrogen. In this nitrogen, how many electrons are there?
3.
Yeah. Wait a second, sorry. 3. You said 3.
No, 2.
Okay, fine. Tell me, what is the atomic number of nitrogen?
6.
No,
No, 7.
learn that first.
7.
7. It is 7. So tell me, how many protons are there? How many protons in nitrogen? And how many electrons? Are Chubena?
Sir,
How many protons in nitrogen?
5.
Why 5? Acha, wait a second. I mean, okay, fine. You skipped the basics in 10th standard or what, I guess. You skipped some basics. So you don't like chemistry from 10th standard only?
No,
9th standard, 10th standard?
I was scared of my teacher.
You were scared of your teacher. Half of the times, yeah, it's true. I mean, the interest on the subject is solely upon the teacher, and obviously the first time how you were taught the subject, it really depends on that. Okay, fine. First of all, every element in its form in the periodic table, if you see any element, it is neutral, first of all. And what is the atomic number? Atomic number is equal to number of proton. Okay, what is the atomic number? Atomic number is equal to, you just count the number of protons and they have just given the atomic numbers. Okay, so now you tell me, if we know the atomic number now, then we can tell about protons, number of protons, right? So how many protons?
7.
7 protons. Okay, and if 7 protons, then from protons, what charge we will be gaining? Plus 7, correct?
Yes, sir.
Okay, now if I have to neutralize this plus 7, then I have to get how many electrons?
Minus 7, like 7.
7 electrons. Okay, so nitrogen has 7 protons and 7 electrons. Okay, cool. 7 protons and 7 electrons, and that is why it is neutral. Okay, so let us take this example of NH3. Now, when anything is bonded, we don't look at inner shell electrons. For example, if I write nitrogen 7, can you tell me about its electronic configuration?
Sir?
1s2, then
2s2,
2p. How many are left? 2p3, correct?
2p3.
3 is left. Okay, that means I will ignore this inner shell electron and I will just take this particular valence shell electron. So how many valence shell electrons are there?
2.
5. 5,
5.
na?
Okay.
2 from here, 3 from here. Okay, and what is the valence shell? Valence shell is equal to 2. It is the second shell. Valence shell is equal to 2. Hence we have 5 electrons in the valence shell. Okay, now in NH3, what you have to do? You have to do minus 5 minus. How many covalent bonds can you see here? How many covalent bonds?
3.
3. Then you have to subtract how many lone pair electrons can you see?
2.
2. So this will be equal to
0.
0. Okay, very easy. Now wait a second. So formal charge is equal to, wait a second, is equal to number of valence electron minus number of covalent bonds minus number of lone pair electrons. Okay, now let us take this example, NH4. Tell me now, what will be the formal charge on nitrogen? Very easy. Now tell me, number of valence electron in nitrogen, Jubaina?
5.
5. And how many covalent bond can you see here?
4.
And how many lone pair electrons can you see here?
0.
So what will be the formal charge?
1.
+1. Okay. Now just remember this. Okay, just remember this. Even though nitrogen is positively charged, it cannot form another bond. I mean, no electrons can attack here. Okay. Why? Because if electron will attack here and the nitrogen will be starting to form a bond, it will be forming 5 bonds, correct? 5 bonds, correct? If we form one more bond, then it will be forming 5 bonds.
Yes, sir.
Okay. Now, if 5 bonds, then how many electrons? One bond has 2 electrons, so 5 bonds mean 10 electrons. Now, this violates octet rule. Correct. So even though nitrogen, it is bonded 4 and it has a formal charge, and that is why it is called formal charge, because it is not real charge. It is just a formal charge. It's for the sake of formality. For the sake of formality. Okay. Now wait a second. I am giving you one more thing. Generally we have carbon, and carbon. What is the next? Nitrogen. What is next? Oxygen. Fluorine. Okay. Now neutral. If you want neutral carbon, it will have carbon with 4 valency. Nitrogen, when it is neutral, it will have lone pair and 3 bonds. Oxygen, when it is neutral, it will have 2 lone pairs and 2 bonds. Fluorine, when it is neutral, it will have 3 lone pairs and 1 bond. Can you see? 4 bonds. 3 bonds plus 1 lone pair, 2 bonds plus 2 lone pair, 1 bond plus 3 lone pair. Okay. Now, if I want, for example, if I want positive charge, cation, the carbon cation will be having 3 bonds. Nitrogen cation will be having how many? 4. You have just saw na?
Yes, sir.
4 bonds plus 0 lone pair. Okay. Similarly here plus 0 lone pair. Oxygen will be having 3. And 1 lone pair will be there. Okay. And 1 lone pair. 3 bonds plus 1 lone pair. Now fluorine cannot form another one. Fluorine cannot form another one. We will just leave it blank. And if I want to have an anion, now carbon will be having 3 bonds plus 1 lone pair. I mean, if you go at home and calculate the formal charges in each of the cases, you will get the same. Now, if nitrogen wants to have, then it will be having 2 bonds, 2 lone pairs, 2 bonds and 2 lone pairs. Now this will give it a negative charge, and this will be 2 bonds, 2 lone pairs. Now, if oxygen want to have, it will have 1 bond and 3 lone pairs. And now nothing for fluorine. Can you remember this?
Yes, sir.
Hannah, it's very, don't note this down. First, let us complete this one. Okay. So you were asking about positive charge now. Now tell me how many bonds in nitrogen? Here, this nitrogen.
5.
5. How 5? 1, 2.
2.
It is hydrogens are also bonded na. Hydrogens are like this na.
Okay, 4, sir.
4, and hence 4. Then just see the table, and you will be memorizing this table by 4 bonds, positive charge. I mean, it doesn't matter whether the bonds are single or double. If there are 4 bonds, that means positive charge. Okay. Similarly, tell me, oxygen here, how many bonds?
4. No,
See and tell.
3.
Good. Okay, fine. Now tell me this carbon here, this carbon. How many?
3.
3 bonds plus how many lone pairs?
0.
Or 1 lone pair is there. See, I have just.
Yeah.
1 lone pair is there. Na? That
Yes,
is
sir.
by negative charge. It is negatively charged. Na? Negatively charged. Similarly, here the carbon will be having a lone pair. I have not shown them, but this carbon will also be having a lone pair. Okay. A non-bonding electron, basically, not lone pair as we have seen in 12th, 11th standard, but a non-bonding pair of electrons. Any further questions, Giovanna?
No, sir. Clear.
Okay, fine. Okay. Note this down. Let me know. Okay. Just remind me, I will let you copy this slide at last. Okay. Now the next case is, we have looked at second. This is our third case. Third case would be pi, sigma, and free radical. A, double bond B, single bond C, and with a lone pair. Sorry, not a lone pair, it is a free radical. What is a free radical? There is 2 type of fission. There is 2 type of fission, homolytic and heterolytic. What is the difference between fission and fusion, Jubana?
So commonly or like chemistry wise?
I mean, whatever you know.
So actually, I don't know how to explain it. I just know fusion. I don't know fission.
Okay, what do you understand by fusion? You know no fusion. Tell me, what do you know?
I don't know whether it's correct or not.
I am asking, what do you know? I am not asking you whether it is correct or not.
Like we say, right? Fusion of colors.
Okay, fine. That means few things are coming together. Correct?
Yes, sir.
Coming together. The fission is just opposite of fusion. It is breaking. Okay, nothing. It is breaking, fusion and fission. Achha, do you have biology?
No, sir.
That is why. Okay, fine. Fission and fusion, the biology people understand it very easily because they have so much of fission and fusions in biology. Okay. So bond break via 2 methods. Bond break. Bonds can break either one case would be heterolytically, and this is called as heterolytic. This is known as heterolytic fission. What is heterolytic fission? It is when A and B are bonded. There are 2 electrons in one bond. Now, when they break apart, what happens is that one of them gets the whole of electron. Both the electrons is transferred to one atom, and the other one is devoid and it is deficient of any atom. Generally, this is the case when En of A is greater than that of B. Okay. The next one case, that is by heterolytic. That means this bond was a hetero bond between 2 different atoms. And when it is homolytic fission, in this we have A with B. And what happens is when the bond breaks, one electron gets transferred to A and another electron gets transferred to B. So we have A, we call this free radical, and B, another, this is also called free radical. And now this is the case generally when En of A is similar to B, electronegativity of similar to B. So now we understand what is a free radical, and this is also, this is what, this is a anion, this is cation. Now what are these? These are free radical. Got it? Are you with me till here?
Yes, sir.
Now let us see what the resonance in these type of free radicals. So let us start with the simplest, CH2, double bond CH, single bond CH2, and a free radical. Now just see how the movement of electron is there. Okay, the movement of electron. Now this bond will be composed of, a second, let me get a bit colorful, 2 electrons. And now this is the, let me color this as green electron. Okay, now what happens is this electrons come here. Now what I'm showing is a fish hook arrow or a single headed arrow, single headed, not double headed, single headed. And what happens is this green one comes here. Now what will happen next? This red one, it will transfer to the carbon. Now I can make the next resonating structure, and the next resonating structure will look like CH2. Now this will be single bond CH, double bond CH2. Now the new double bond which has been formed is formed by the red and the green electrons. The red and the green electrons, and one of the red electrons is now as free radical in this carbon. Okay. Now what will be the resonance hybrid? The resonance hybrid will be, which is another color, yes, CH2 with a single bond CH, single bond CH2. Now both of them, this single bond will be having a partial double bond character, and delta free radical here, delta free radical here. Okay, are you with me till here? Now let me tell you what happens in between these two structures. In between these two structures, there is one structure which is like this. CH2 with a free radical here, and a CH with a free radical here, and a CH2, the free radical here. Okay. Now what happens is this is very unstable. And then easily it forms a bond like this. So one thing that you have to understand is for the movement of, just take care of this always, for the movement of one electron, always use fish hook arrow, or it is also known as single headed arrow. Single headed arrow. Are you with me, Rebecca, till here? Okay, fine. Wait a second. If you want to copy, then copy from here. Acha. Jubena, I was thinking you will be turning your audio and telling yes sir, no sir. Okay, fine. I just received the chat.
Okay, sir.
Okay. Okay, Jabana, it's fine. Okay, Fatima has joined now. Can you get a gist of this, Fatima? I hope you are able to understand what is written on the screen. I've just written the bonds can break in two ways. Either heterolytically, that means all the electrons of a bond is transferred to one of the atoms, and that gives us a cation and an anion. And the other case is homolytic fission, in which the bonded electrons, the electrons that were present in a bond, and it is always two electrons in a bond, one of the electron goes to one atom, another electron goes to another atom. And in that case, we form free radicals. Fatima, are you with me till here? Okay, fine. If you have noted this down, let me know. I will go to the next slide. Yes, Jubana. Are you done noting this down, Jubana? Okay, fine. Just remember this, that this is resonance hybrid, okay? This is resonance hybrid. RHS, resonance hybrid structure. This is resonating structure, that is also resonating structure. Let me know when you're done completing this one. You're done. Meanwhile, yes, I can give you a few questions that you can try. Okay, fine. Yes, so you are done, then try these. Try this one. We have a benzene here and a CH2 free radical here. You have to make the resonating structure and tell me number of resonating structures. And the next case that you can do is this one. And then you have to tell me number of resonating structure for this one. Try these two and let me know the number of resonating structures. Let me give the numbering also. This is question number 1. This is question number 2. I mean, 4 more resonating structures, correct, Jubana? You're trying to say 4 more resonating structures, correct?
Yes, sir.
And if I include this one also, it will be 5. Total will be 5 and 4 more. What about the second one?
Doing, sir.
Okay, okay. And so even for the second one, 4 more. So let us see. The first one I can see it like this. And then so I can see just 2 more, Jubena.
Okay, sir.
Where did you went wrong?
Change. I just changing of double bond. I did same thing twice.
So you have 2 same resonating structures, exactly same, correct?
Yes, sir.
That's okay, fine. So 2 more only. That would be 3 resonating structures in total. 3 resonating structures in total. Okay, fine. So I'm moving now. The next one is, okay, this was third one, I guess. Yes, the fourth one will be, fourth is pi sigma pi. This means A double bond B, single bond C, double bond D. Okay. Now, the easiest example for this one, will be CH2 double bond CH, single bond, what it would be, CH only, then we will have a double bond and an oxygen. Okay, see, tell me how many bonds of oxygen are there in this particular molecule, Jobana? How many
2.
oxygen? 2. And that is why this will be neutral. This will be neutral. Okay. Now, how to move electrons here? How to move electrons here? What do you think?
I guess from CH.
Like this. From here, it will move from here. Wait a second. This is aldehyde group, if you can see. Aldehyde is carbon, which is bonded to oxygen. Generally, we write it like this, na, CHO. Right? CHO group, aldehyde group. If I want to write it like this, double bond O and H. Double bond O and H. Correct?
Yes, sir.
Okay. Aldehyde group, just remember this, huh? Aldehyde group can have resonance. I'm writing it like this now. So now what will happen? This particular bond will shift here. First, this will happen. To C, double bond CH. This CH would be, now the electrons are going to oxygen only. That means oxygen will be now negatively charged. One bond. Here it has 2 lone pairs. Now here it will be having 1, 2, 3 lone pairs. Wait a second, I have to make lone pair a bit separated. Yes, yes. Now this carbon will be having a positive charge, right? Because initially it had how many bonds? It had 4 bonds. Carbon bond from here, 2 bonds with oxygen, 1 bond from hydrogen. Now it has broken 1 bond. That means it has 2 bonds and 3 bonds and no lone pair, and hence a positive charge. 3 bonds and no lone pair, hence a positive charge. Now simple is the case like this. H2C, single bond, CH double bond CH, single bond O negative. O is having 3 lone pairs. And now this carbon will be having a positive charge. Now you tell me, what is the total Q? What is the charge here? Total charge here?
It's
What is the total?
neutral.
Huh?
Neutral.
Total charge? Neutral, 0. What is total charge here?
0.
0. Here also?
0.
0. Now the resonance hybrid for all this will be, just wait a second. Huh? See, CH2, CH2, no, CH, CH, and sorry. Oh, this was the skeleton. Wait a second. I'm just writing this again. It was very bad handwriting. Wait a second. I'm writing this again. Double bond CH, single bond CH, and O. I'm just removing this particular pi bond because this can move, right? Now you tell me, now this two carbons has a pi bond here, a pi bond here, but no pi bond here. That means a partial pi bond here, correct? This bond is partial pi bond. It is not, because all the resonating structure is not having this pi bond. I can write it like this, okay. And this carbon here is neutral. This carbon here is also neutral. This carbon here has a positive charge. That means it will be having a delta positive charge. Now move to the next carbon. This carbon has zero charge. This carbon also has no charge. This carbon also has no charge. That means this position carbon is neutral. Okay. Now let us move to the next carbon. This carbon is neutral. Now this carbon here has a positive charge. That means this will be delta positive. Okay. Delta positive. Now what about oxygen? Oxygen here has no charge, but oxygen here has a negative charge and here also negative charge. That means it will be having delta negative. Okay, and all the bonds, see this bond is single, but here it is double, so partial double bond. This bond here is double bond. This bond here is single bond. This bond here is single bond, but once it is double bond, it will be partial double bond. Okay, now Jubana, do you understand this resonance hybrid structure?
Yes, sir, got it.
But wait a second. Now wait a second. See the beauty of chemistry now. See the beauty of chemistry. Okay.
Okay, sir.
CH2 double bond CH double bond O. Okay. Now if somebody asked, where is the electrophilic center? That means if I get an electron source, if I get a nucleophile, if you remember from the last class, nucleophile, where can it attack? Where will it attack? It will attack in first position, second position, third position, or fourth position. Tell me, where will the nucleophile attack? It can attack on
CH2.
1, 2, 3, 4. Tell which one?
1.
It can attack on one position. Why? Because it has a delta positive charge. Okay. But was it visible from this structure? From this structure, was it visible?
No, sir.
No, no. That is why, that is like chess. It's, so many underlying things are happening. Okay. It can attack on one position also, and it can attack on third position also. Correct? Because this third position also has a delta positive charge. But we are very sure it will never attack here. It will never attack here, and it will never attack here, because this is neutral, and a nucleophile will never attack a neutral atom when it has a chance to attack on the positively charged atom. And obviously nucleophile is electron rich, electron source, and oxygen is delta negative. And if it is delta negative, it will repel the nucleophile and it will not attract the nucleophile. So you have two positions. We have two positions in which the attack can happen. Okay. So this was the beauty. This was the beauty. Underlying things, subtleness of chemistry. Okay. So just write this. If you want to write the nucleophile and electrophile thing also, then it is fine. Either here or here, but not here and here. Just note this down. Fatima and Afroza, did you get this? Achha, not properly. Fatima, if you can just, were you present in the last lecture when I discussed about electrophile and nucleophile? Achha, fine. So electrophile and nucleophile, you understand that nucleophiles are nucleus loving. That means nucleus loving. That means it will attack on the proton in the nucleus, on the electron deficient side. And I said that nucleophiles are electron rich. Correct, Fatima? Yes. So if it is electron rich, it will attack on electron sink. Correct? Correct, Fatima? Now, what is the electron sink? Wherever, oh, do you understand this? What is electron sink? Electron deficient. That means it will it will be having some kind of positive charge. It will be having electron deficiency. So from the resonating structure, did you understand this resonance hybrid, by the way, Fatima? Okay. Now from this resonance hybrid structure, I'm just marking the carbon as this carbon is A carbon, this is B carbon, this is C carbon, this is D carbon. What do you think? Which of the sites, which of the carbons are electron deficient? B is electron deficient. If I ask you why B is electron deficient? So you just guessed it. Okay, fine. Electron deficient. Okay, electron deficient. This will mean that less negative charge, correct? I can say that if it is electron deficient and electrons are negatively charged. Okay, fine. If I say less negative charge, then what I am saying indirectly is more positive charge, correct? Okay, fine. Then if I ask you electron deficiency, then you have to look where is the positive charge, correct? So now you tell me which of the carbons are electron deficient? Which of the carbons are electron deficient, Fatima? Yeah, you can see a delta positive charge here. So this is C, correct? And also A, right? A is also positive charge. Okay, now is it clear how to locate the electron deficient site? Okay, fine, great. Okay, great. Just ask Fatima, okay? And don't wait for me to just engage you in a conversation. You can ask at any time. Yes, we were doing. Okay, fine. Now let us do some more examples. Now, this will be like this. So this will be O, this will be negative. Now wait a second, let me just put the lone pairs here, okay? This will be positive on here. Then we can make like this. And a bond here and a positive charge here. Okay. By the way, did you all copy this slide? Fatima and Jubaina, did you copy this slide? Okay, fine. What more examples can we see? More examples can we see are CH2, double bond CH, single bond CH, and a double bond CH2. So what will happen here? Like this. And in one go, you can show it like this. So this will be C. This will be positive charge, single bond CH, double bond CH, and then single bond CH2 negative, CH2 negative. So if I want to say the resonance hybrid structure, the resonance hybrid structure will be looking like this: CH2 and not a double bond. Wait a second, just let me draw the skeleton. CH, single bond CH2. This is double single. That means this is all these are partial double bond characters, and one of the carbon has a delta positive charge, and this will be having a delta negative charge. If this is a delta positive, this is delta positive. This will be delta negative. This will be delta positive. Okay. I mean, if you draw the intermediate structure, you will get this as the resonance hybrid structure. Okay. Done writing this one. Are you done writing this one? Okay, fine. Right. Okay, done, Fatima. Great. Now the last case that I want to, the last case is if we have a lone pair. I guess this is which case? Fifth case. We will be having some lone pair electrons, then a sigma bond, then a positive charge or vacant orbital. Example of this would be CH3, and if we have NH and single bond CH2 positive. Single bond CH2 positive. Then what resonating structures can we make here? We can make this structure. Now what is happening here? CH3, the nitrogen lone pair is moving. So nitrogen is forming a bond here. Now as soon as nitrogen has 4 bonds, what will be the charge, Jubena, for nitrogen?
Sir?
Nitrogen has how many bonds here?
4.
So that means positive charge, correct?
Yes, sir.
Now what will be the resonance hybrid? Nitrogen, double bond CH2. Oh no, not double bond, sorry. Single bond CH2. And this will be a partial double bond. This will be H. This will be delta positive, correct? And this will be delta. This will be also delta positive. Now, what is the total charge here?
Positive.
What is the total charge, Jubena?
Positive.
Yes. 1 plus 1. Here?
Plus 1.
Plus 1. And here also?
Plus 2.
Plus 1. Everywhere it is plus 1. Similarly, no, not plus 2. Delta means small, no?
Okay, sir.
Delta means small. And if you remember my last class, just remember my last class. In the last class, what I taught, how to give exact number of the charge, the fractional charge, how to give that. You see the number of resonating structures. There are 2 resonating structures in nitrogen. In how many resonating structures there is a positive charge in nitrogen? So, and divided by that. Total resonating structures, and one of them has positive charge. That means N will be having plus half, carbon will be having plus half. If I want to say the exact fractional formal charges, correct?
Yes, sir.
So what will be total? Plus 1 only?
Yeah, plus 1, sir.
Now this one will be similarly drawn like this. It has double bond CH2, and this has now positive charge. So the resonance hybrid will be CH3. Oh, sorry. O and a partial double bond CH2 delta positive. Got it? Now let us wait a second. Just wait a second. We will do one question. One question. We will look at one more. Then we can move on. For example, if I have like this CH2 positive, and I have bonded this with a CH. This CH is double bonded to another CH, which is bonded to O and H. It's bonded to O and H. Okay. And this oxygen will be having two lone pairs. Now this can go conjugation here like this. Now what will happen? H2C single bond C. Now this C will be having a negative charge now. The CH will be having a negative charge now, as we have drawn here. And then we will be having this CH, which is double bonded to oxygen and a positive charge here and hydrogen. And this was always positive here. Now what will happen? As I said, if carbon is getting electrons, a negative charge, that means it is also getting a lone pair. It means that it is getting a lone pair. Means that it is getting a lone pair and it is generating negative charge. Now this will go here. I can make one more resonating structure like this. H2C double bond CH single bond CH. Now this will be double bond and H, and this will be positive. If I want to draw the resonance hybrid CH2 CH single CH, now single bond OH. Okay. Now can I have Jubana, please?
Sir.
Hello, Jubana, you there?
Yes.
Now you tell me. We are just looking at this carbon. Okay. Now tell me, this has positive charge here, correct?
Yes, sir.
Positive charge here, correct?
Yes, sir.
And it is neutral here. That means what charge should I give it here? Delta
1.
Delta positive charge here, correct? Now let us tell me about this carbon. Neutral. Now here it is negative. And here it is neutral. So delta negative. What about this carbon? It is neutral. So here it will be neutral. What about oxygen? Oxygen is neutral. It is positive, and again it is positive. That means delta positive. Okay. Now you tell me about this bond. It is single bond here.
Yes, sir.
Again single bond here.
Yes.
Now here it is double bond. That means this will be partial double bond. Correct?
Yes, sir.
And now tell me about this one. Partial double bond or complete double bond?
Partial double bond.
What about the next one?
Single bond.
This one will be single. This is single. Here it is double, no?
Oh, okay.
Here also partial double bond. Okay, that's it. Now nothing is changing with OH. OH is same, but a delta positive in oxygen. Okay, let's note this down. Then let's note this down. Then we will look at some of the which of the resonating structure is most stable. We will look at that criteria. Now, the next topic is stability of resonating structures. Stability of resonating structures. So what do I mean by stability of resonating structure? As you can see, when we draw resonating structures, all structures are not equal. They look like different molecules, right, Jubana? They look like different molecules. That means the stability of each of the resonating structures may or may not be equal. So we have to come up with some criteria, some rules to recognize which of the resonating is more stable. And why we want to do that? We want to do that because the most stable resonating structure will have the most contribution in the resonance hybrid structure. So the first point is, not all resonating structures are identical. Not all resonating structures are identical. Some resonating structures are more stable than others. Okay. Next point is, the most stable resonating structure, has most contribution in the resonance hybrid structure. In the resonance hybrid structure. Okay. What do I mean by identical and non-identical? Identical resonating structures. Example would be very the example that we have already taken. That will be of CO3 2 negative. CO3 2 negative. If I make another resonating structure, it will be like this. Carbon, a double bond, oh sorry, not. This will be single bond O negative and a double bond here. Oh, a double bond here and a single bond here and O negative. Now what we can see from these two resonating structure is that both of them has same charges on the same atom. Correct? Jumana, can you see that? The charges are on the same atom.
Yes, sir.
Now what is non-identical? Non-identical, for example, if I have something like this, let us take yes, this one, this example here. This was double bond O and this was like this. So it moved here and we got a resonating structure like this. Single bond O, negative, positive, and double bond here. Then we have moved these electrons here and we got this structure. Now this single bond O, negative, is same. Now this is a double bond here and a positive charge here. Correct? Now tell me, charges on atoms differ in different resonating structures. Correct, Jubana? They are different in different resonating structures, correct?
Yes, sir.
So now this is identical and this is non-identical. This is identical. This one is identical resonating. This is non-identical. Now identical resonating structure, both of them have same stability. Same stability. Okay, same stability. But the resonating structures which I have drawn in non-identical resonating structure, these are not same. These are not same. So now we will study some rules. We will study some rules, and then we will do some practice problems. Okay, so I'm just writing the rules now. Rules for stability of resonating structures. Just wait a second. So the first rule is the more the number of, first rule is stability directly proportional to number of covalent bonds. What does that mean? It means that more covalent bonds leads to more stability. More covalent bond will lead to more stability. Okay. Now the next thing is, this is very easy rule. Neutral species are more stable than charged species. Okay, neutral are more stable than charged. Now, what is the third one? Third one is that the negative charge, if you have any negative charge on electronegative atom, generally it is fluorine, oxygen, nitrogen, chlorine, bromine, etc. Okay. Negative charge on electronegative atom is stable, and positive on positive charge on electropositive. I mean, if you don't write electropositive, it is okay. If you have a negative charge, just remember to put it on. If it is on electronegative atom, then it is more stable. Now the last point is two like charges in a resonating structure should be far apart. Fifth rule is two unlike charges. This will give us stability. Two unlike charges in a resonating structure should be close together. Now, if it is close together, this will give us stability. There are five things. First of all, you have to count the number of covalent bonds, and you will go in the sequence. I mean that if you have found the resonating structure, you have compared the covalent bonds, and there is more covalent bond in one of the resonating structure, that particular resonating structure is more stable. Now, if you have the same number of covalent bonds, then you will see which is neutral, which is neutral and which is charged. The neutral one will be more stable. Now, if both are neutral or both are charged, then you will see where is the negative charge. If the negative charge is in the electronegative atom, then it is stable. If the negative charge, the resonating structure which has the negative charge on the electronegative atom, it is more stable. And the resonating structure which doesn't have negative charge on the electronegative atom is less stable. And if you have that also same, then you will see the two like charges, whether the two like charges are far from each other or they are closer. If they are closer to each other, the like charges closer to each other will give us instability. So they should be far apart. And the unlike charges should be close together. So just write this down. First of all, this one, if you have not written this one, then the next slide, then we will do some questions. And I guess by the end of questions, time would be up. Just let me know if you're done with this one, this slide. Fatima and Jubaina done? What about Jubaina? Fatima has done. Okay, fine. I guess both of them at the same time. Now write the rules. Write the rules for stability of resonating structures. If you're done with this one also. Then Jubaina, what about Fatima? Fatima done? Okay, fine, great. Now I'm giving you a series of questions. Okay, series of questions. Start writing those, and then when I have done with the questions, I will ask you. I will do one of them, and then you can proceed on. What is the question? Which of them? Which of the? Not which of the. Write the order of stability of following resonating structure. Okay, so the A question, the first question is CH3, O, and CH2 plus. Now it is in resonance with like this. This will be CH3, single bond O, double bond CH2. This will be positive charge. Okay. Now, okay, I will write it like this. Wait a second. This is A, this is 1 and 2. The question B is you have to compare between 1 and 2. The next question is CH2, single bond CH, yes, and a single bond NH2. Now the resonating structure would be like this. CH2. Now this will be having a negative charge, single bond, CH, double bond, NH2 positive. NH2 positive. Now you have to look at the C question. You have to compare between, again, this is 1, this is 2. You have to write the order, which one is more stable. Next question, if I take similar thing, CH2, double bond CH, and we get O negative, then this will be like this. CH2, this will be negative charge, CH. Now this will be double bond. Okay, sorry for that. This will be double bond O. This will be double bond O. Yes, okay, fine. Next question, if I say, let us arrange this one. C double bond O, O negative, O negative, and if I say something like this, C double bond O negative, O negative. I move the charges from here to here. Okay, from here to here. So this will be O negative, and this will be positive. And let us say similarly, but just opposite charges. One, 2, 3, 1, this is 2. Okay, now I have to use this space. Just keep noting this down. Just keep noting this down. Okay, now what else should I give you? Just put some acid here now. H. HC, HC, double bond O, OH. So one structure. If I make another structure, let us do it like this. HC, O negative, double bond O, H positive. Next structure, how can I make it? Okay, fine. H, C, single bond O, and let me write a single bond O here also, and H. If this is single bond, then it is fine. OH is fine, and this will be negative. This will be positive. Okay, it's great. This is the third structure. The fourth structure that I can make is H, C, O positive, C negative, OH. It's the E question. Let me see if I can I make some more? I can say I can make some more. Okay. Last question, F. CH2. Double bond N. Double bond N. And let us write it here, negative charge, positive charge. Now this negative and positive would be familiar because this nitrogen has 4 bonds. This nitrogen has 4 bonds. This is first structure. To compare it to another structure, let us write it like this. CH2, single bond nitrogen, double bond nitrogen. This nitrogen is negative charge here now. This nitrogen is neutral because it is having 3. Now this carbon will be getting, let us say like this, a positive charge here now. It should be neutral now. So this is structure 1. This is structure 2. What else structure can I make? Yes, I can make another one like this. CH2 negative and single bond nitrogen and a triple bond nitrogen here. Now this nitrogen, when it is having 4 bonds, a positive charge will be there, and this nitrogen will be neutral because it is having only 3 bonds. 3. Now, if you see all my resonating structures, they have the net total charge is same in all the resonating structures. Okay, what else? What else I can make? I can make this also. CH2 negative, and if I get a nitrogen here, a double bonded nitrogen here, then this will be positive because it has only 2 bonds. This has 3 bonds. This has 3 bonds. Okay. Now, yes, do tell F, and then if you are done, okay, fine. Tell me which of the questions should I do for you? Which of the questions? A, B, C, D, E, F. Order of stability. Fatima and Jubaina. Look for a moment in the screen. If you are copying, just hold and pause the copying. Yes, tell me. A, B, C, D, E, F. Which one should I do? Fatima, Jubaina, is anyone here? Are you listening or just copying? F. Okay, fine, Jubaina, F. Fatima, Jubaina has said F. So you agree? There is F. What do you have? An F? Okay, fine. I have to write. I'm just using another slide and I will write these structures. I'll write these structures. So the structures is like this, I guess. CH2, bond N, double bond N. This will be plus, this will be minus. Then we have another one. Okay, fine. Let me write like this. We have CH2 positive here and 1 nitrogen and double bond nitrogen, and this one is neutral. This one will be negative charge. Then CH2 negative, I can have 2 more CH2 negative. This I can have okay, nitrogen, triple bond nitrogen, and this will be positive charge. And again, I can have CH2, CH2, yes, CH2, negative charge, and a single bond here, and a double bond here. So this will be neutral, and this will be positive. Can this happen? Yes, it can happen. It can happen. CH2 negative and positive. Yes, fine. Okay. So first of all, Jubaina, can I have you, please?
Sir.
Number of covalent bonds. Tell me number of covalent bond in this one, the first one.
2.
Huh? How many bonds can you see?
0.
0 bonds?
No, double bonds are there.
No, tell me number of bonds. Covalent bond or double bond, single bond, any type of bond. How many bonds can you see?
2.
2 bonds.
Yes, sir. 2 bonds.
Only 2 bonds. What about Fatima? How many bonds, Fatima, in the first structure? Jubaina, how many bonds now? AB between A and B?
1. Okay, 4.
Why do you say these things? Are you somewhere else?
No, sir.
Okay, this has 4. Now, what about this one? How many here?
3.
3. What about this one? How many here?
There 4.
4. What about this one? How many here?
3.
Huh? 3. Okay, fine. Fine. And that means I can say that now the fight is between 1 and 3, and there is another fight between 2 and 4, because the number of covalent bonds is same for 1 and 3, and it is also same for 2 and 4. Okay, fine. Now the next thing, what is the next thing in our rules? See, neutral species are more stable than charged species. Now let us see if yes, all of them are neutral, na? Positive, negative, positive, negative, positive. The net of the net charge is neutral. All of them are neutral. I mean, this is also positive. This is also negative. Positive, negative, positive, negative. Okay, fine. None of them is neutral. No neutral. So let us move to the next one. Negative charge should be on electronegative atom. Okay. So here, I will write the next column as negative charge. Now tell me, where is the negative charge in this particular in first structure? Negative charge in nitrogen. What about here, where it is?
Nitrogen.
Nitrogen. What about in the third case? It is in third structure. Where is the negative charge? Sorry, I didn't get you. Where is the negative charge?
CH2.
Yes, CH2. It is on carbon. It is on carbon. Okay, you will not say CH2, you will say carbon. Okay, from now. What about the fourth structure? Where is it? Yes, correct. Carbon. Now we are done. Just now compare. Okay. 1, 2, 3, 4. Who were the winners? 1 and 3, right? Because they have 4 covalent bonds and 4 covalent bonds. If 1 versus 3, who were who won in 1 versus 3?
1.
If we saw the negative charge, nitrogen, so 1 is winning. 1, then 3. Okay. Now we have 2 versus 4. Correct? 2 versus 4. Why? Because number of covalent bonds and number of covalent bonds are same in both of them. Now we will look at what is the negative charge. Where is the negative charge? So in 2 it is on nitrogen. In 2 it is on nitrogen, and in 4 it is on carbon. That means 2, 1. Yes, 2, 1, 4. Easy. It is systematical.
Yes, sir.
Okay. Now you can try
Okay, sir.
these all. If any of the structure is not visible, just let me know and I will correct it. Okay. If it is, I will just clear it out. And please, okay, fine. I'm seeing your chat also. You can tell me which I can redraw some of these structures if you want. Okay. 5 minutes. Let me tell yes. Also, just see how I did it in a very systematical, a very organized way. Please do it in the same way. Okay. Don't start counting in the structure here only. Don't do that. I mean, by the end, you will be able to do that. But for now, for starters, you have to write number of covalent bonds, then compare the negative, then compare whether it is neutral or charged, then compare whether it is, where is the negative charge, then at last compare the charge separation. Okay, Fatima, Jovana, do it in a proper way, writing everything. Okay, take time now. I'm giving you 10 minutes. Okay, 10 minutes I'm giving you. Okay, Jubana, that was fast. Okay, Fatima has given me the answer. Okay, Fatima has given me the answer. What about Jubana? Okay, Jubana has started to give me the answer. Okay. Okay. Two one. Okay, Jubana. Then okay, fine. Let us see for the first one. Okay, let us see for the first one. Okay, Fatima has changed one of the answers. Fatima has changed one of the answers. Let me see. Okay, fine. Fatima has changed one of the answers. Just compare it with your answers now. In the first one, 2 is more stable. Why is 2 more stable? Because of number of covalent bonds. Correct, Fatima, Jubana? Okay, let me just write the answers why each one of them is more correct. In the first question, in the A question, 1 is more stable due to more covalent bonds. Correct? Yes, Jubana?
Yes, sir.
What about in B? Second question.
So 2. 2 is more stable, right?
Why 2 is more stable? Let us see the question now. Neutral. Are Fatima, 1 is neutral, 2 is charged, 2 is having charges, 1 is having no charge, na? Correct, Jubana?
Yes, sir.
Which is charged? 2 is having charges, 1 is neutral. Correct.
Yes, sir.
So the next one, in B, 1, I can say the second structure is less stable due to charge. A, B, and C.
Yeah,
Now what about C?
2 of
In
1 is
C?
stable. Is it
Sorry?
2? In first one, which is more stable?
1 is more stable, no? 2 is less stable. In this one, 2 is more stable than 1. Let us see C. Let us see C. Got it, Jabana, about the second question, about the B question?
Okay, sir.
Now, what about C? Which is more?
I guess I gave 1 is more stable.
1 is more stable. Why?
Because a negative sign is on oxygen.
Electronegative atom, correct. 1 is more stable due to negative charge on oxygen. On oxygen. So what I have to write, 1 greater than 2. Okay. Now the D1. Let us see the D1. What about D1?
My order is 1, 2, 3.
1, 2, 3. Same is for Fatima, I guess. Same is for Fatima because 1 has the most number of covalent bonds, and this one here has a negative charge. That is why it is more stable than the third one. The covalent bonds in 2 and 3 are same, but the negative charge is on oxygen in the second structure. That is why it is more stable. 1, 2, 3. E. What about E? What is your answer?
2,
E
1,
is
4.
2, 1, 3, 4.
Yes, sir.
Okay. Okay, fine. Why is 2 most stable?
Because okay, 2 and 1 has like 4 bonds,
Okay.
and then
Then
out of 2, while comparing 2 and 1, oxygen is the electronegative one, so it is more stable.
oh, you missed the second rule, na? What is the second one? Neutral species are more stable than charged species.
Okay,
So
sir.
which is neutral? 1 or 2? Which is neutral?
1.
Yes. So got it now?
Yes, sir.
Then 1, 2, because now why 2? Because number of covalent bonds. Then between 3 and 4, these two have same number of covalent bond. Between these two, 3 is more stable because electron negative atom has negative charge. Correct?
Yes, sir.
Okay. So the correct order will be 1, 2, 3, 4. Simple. Okay. I'm glad that you all did it. Okay, fine. So I'm ending this class here. Okay, I'm ending this class here. Then we will be doing mesomeric effect in the next class. Mesomeric effect and hyperconjugation. I hope I can do this in one class. Hyperconjugation and mesomeric effect. Then we will have a bit of look on the intermediates, carbocation, carbon ions, and free radicals. Then we can start, I guess, alkyl halides. So I guess after 2 more lectures, the GOC, general organic chemistry, will be over. Then we can start alkyl halides. And things will be having, you will be doing organic chemistry in just, what can I say, chutki mein, if you understand chutki mein. Snap of a finger. Okay. For now,